Hello everyone, I am Mary Swarnalatha, working as an assistant professor in the Department of Electronics and Communication Engineering. In today's lecture, we are going to discuss about the conditional distribution and density function. In the conditional distribution density function, again we are seeing the two types of conditioning. One is point conditioning, the other one is interval conditioning. After that, we'll see the properties of the conditional density function. So, what is the condition probability? So, already in the previous lectures, we have seen the condition probability of an event B and given the event A. What is the formula here? P of A intersection B by P of A. So, here, what is P of B by A? Which is called as what? The conditional probability. So, the conditional probability of the event A. And what is conditioning event here? The event is A. Is nothing but P of A intersection B. That is nothing but the probability of the joint event A and B to the probability of the event A, the conditioning event A. And in a similar manner, we can apply for the distribution function also. What is the distribution function actually? The distribution function of a random variable x has been defined as the probability of the event x is less than or equals to x. So, for example, the event x is less than or equals to x, let us say, has been denoted by the symbol b. So, now what is the event b? That is nothing but the event, the random variable x takes less than or equals to x. Then what is fx of x here? That is nothing but p of b. This is called as what? The distribution function of the random variable x. And similarly, if you want the conditional distribution function of the random variable x and given the conditioning event A, then how can you write as fx of x by A? So, what is fx of x by A? Here, what is capital X represents? The random variable. So, what is capital F represents? The distribution function. Since here you are given the conditioning event, you can call it as what? The conditional distribution function of the random variable x and given the conditioning event is A is equals to what? P of x less than equals to x by A. So here, so what is P of B by A? That is nothing but what? Here we have seen P of B intersection A by P of A. So here, in place of B, what I am having here? X is less than equals to x intersection A by P of A. So this we will call it as what? The conditional distribution function of the random variable x and given the conditioning event is A. So P of x less than equals to x by A. So what is, let us say this is like B, then what is P of B by A equals to P of B intersection A or A intersection B by P of A. So P of x less than equals to x intersection A by P of E. And in a similar manner, you can define the conditional density function. How can you define the conditional density function? We know the definition of the density function of a random variable x. What is the definition? The differentiation of the distribution function gives the density function. This is the relation between the density function of a random variable x and similarly the distribution function. In a similar manner, you can define the conditional density also. So, how can you define the conditional density? The conditional density function of the random variable x and given the conditioning event A is equal to the differentiation of the conditional distribution function of the random variable x and given the conditioning event A. Now, here the conditioning event A. So, the conditioning event A is defined in two ways. One is what? Point conditioning. So, one is point conditioning and second one is interval conditioning. So, you can define the conditioning event A in two ways. One is what? Point conditioning. The other one is what? Interval conditioning. Now, what is point conditioning? The point conditioning is nothing but, so the conditioning event is defined in which random variable? I am defining the conditioning event on the random variable y. Now, how I am defining here? A is equals to what? Y minus delta y less than y less than equals to y plus delta y. Here what is delta y? It is very small and is approximate to 0. So the name point conditioning is defined such that point is nothing but the random variable y takes a particular value. For example, y is equals to what? Small y. What is here? Y represents the random variable, and what is small y represents a particular value of the random variable y. So point conditioning is nothing but the random variable y is taking a specific value or a point value. Now, in order to derive the conditional distribution density function in case of the point conditioning, I am defining the point conditioning event as y minus delta y less than equals to y plus delta y. What is delta y here? It is approximate to 0. If it is approximate to 0, then what is random variable y is equals to here y, because y minus delta y nothing but y less than equals to y. That is nothing but the random variable y is equals to y. So the same thing I am defining like this. The point conditioning I am defining in terms of the interval. There is nothing but y minus delta y to y plus delta y. Now in place of a, what I have defined here? Fx of x by a. What is a here? Y minus delta y less than equals to y plus delta y is equals to what here? That is nothing but what? P of x less than equals to x by a. What is a here? In this equation, in place of a you substitute y minus delta y to y plus delta y. So y minus delta y to y plus delta y. Now let us say this is the event B and this is the event A. Then what is P of B by A equals to P of B intersection A by P of A. Therefore, what is B here? X is less than equals to X intersection. What is A here? Y minus delta y less than equals to y plus delta y by P of A. What is A here? Y minus delta y to y plus delta y, the random variable y takes. So this is called as what? The probability of the joint event x less than equals to x and y minus delta y less than equals to y plus delta y. Therefore, so we have seen the joint distribution function of the random variables x and y. What is the formula here? P of x less than equals to x comma y less than equals to y. That is nothing but what? P of x less than equals to x intersection y less than equals to y. So we have seen the joint distribution function definition in the previous lecture of the random variables x and y. So here, what are the two random variables here? One is x and the random variable is y. Therefore, this I can define as what? And it is a probability of the joint event. Therefore, this can be written as what? The joint distribution function f x y. What are the two random variables here? X and y. So fxy of here x less than equals to x is nothing but x. In place of y, what I have here? In place of y, I have y minus delta y less than equals to y plus delta y. So this is a joint distribution function. In place of y, I have y minus delta y less than equals to y plus delta y by P of A. So in place of A, what I have here? Y minus delta y less than equals to y plus delta y. So what is fx of x? Already you have seen here. Fx of x is nothing but the distribution function of the random variable x is nothing but what? The probability of the random variable x takes less than equals to small x. Now in place of x here, what I have here? Y. Therefore this is nothing but what? Fy. So fy of, in place of small y, what I have here? Y minus delta y less than equals to y plus delta y. So what is actually fy of y? Fy of y is nothing but what? P of y less than equals to y. So in place of y, I have here y minus delta y less than equals to y plus delta y. Just replace in place of y. Therefore, this is what? The distribution function of the random variable y, and this is nothing but the joint distribution function of random variables x and y. Now, from the properties of the distribution function, the density function, what can you write here? So, what is the properties of the probability density function? You can write the distribution function in terms of the density function. What is that? Integration minus infinity to x fx of u into du. So they can write down the distribution function in terms of density function. So from the properties of what? The joint density function. Similarly, we have seen the properties of joint probability density function in the previous lecture. What is that? The joint distribution function of the two random variables x and y can be written in terms of the density function. The joint density function as what? Integration minus infinity to x here. And the y limits are integration minus infinity to y fxy of u comma v into du into dv. Now we just compare this equation here. In place of x here I have x only. In place of y I have here y minus delta y to y plus delta y. Therefore, what can I write here? Here I can write as what? Integration. What are the y limits? Previously minus infinity to y. And here what are the y limits here? Y minus delta y to y plus delta y. And then what about the x limits here? Here the x limits fxy of x. Nothing but what the x limits? Minus infinity to x. The x limits are from minus infinity to x. fxy of u comma v into du by du into dv. By what is the denominator here? Have fy of y minus delta y less than equals to y plus delta y. Now here in place of x here I have what? Y. Therefore this is nothing but what? Fy. Okay. And in place of x here I have what? Minus infinity to x. If it is fx of x, then nothing but p of x less than equals to x. It is nothing but minus infinity to x. But in place of x here I have y minus delta y to y plus delta y. Therefore the limits here y minus delta y to y plus delta y fy of v into dv. Now for point conditioning, what I told you that the random variable y should take a specific point or specific value. So this is possible in case of delta y to 0. Therefore substitute delta y equals to 0. Then you can rewrite this equation as integration minus infinity x fxy of u comma. So this random variable y is taking a single value. Therefore in place of this what can you substitute here? Y. So fxy of u comma y. Previously it is taking the limits, the interval y minus delta y to y plus delta y. If this delta y tends to 0, it is taking a single value. Therefore fxy of u comma y into du by. So here previously it is taking the random variable y taking the interval y minus delta y to y plus delta y. But in the case of point conditioning, if I substitute delta y to 0, then this random variable y taking a single value of y. Therefore, this is nothing but what? Fy of y. So therefore, this is what? The conditional distribution function of the random variable x. So this also can I write as fx of x by y also. The other representation of fx of x by y equals to y is nothing but what? Fx of x by y. Now, if you want the conditional density function in case of point conditioning, what you have to do? So, if you know the conditional distribution function, how can you obtain the conditional density function? By differentiating. Therefore, you just differentiate this equation. There you can get the density function. So, what is the denominator here? Fy of y, nothing but it is taking a single value. So, the denominator is constant here and the differentiation of the numerator. What is the numerator here? Integration minus infinity x fxy of u comma y into du. So, differentiation of this minus numerator is what? Integration minus infinity x fxy of u comma y into du. So, what can you obtain? This is nothing but what? Fxy of x comma y. Therefore, you can obtain the conditional density function by differentiating the conditional distribution function. Therefore, what is fx of x by y equals to y? That equals to what? Fxy of x comma y by fy of y. So, this can also write as what? Fx of x by y. Similarly, can you write down fx of y by x? What is fx of y by x? That is nothing but what? The conditional density function of the random variable y such that the point conditioning such that the random variable x takes a single value x equals to x. So fy of y by x equals to x, there is nothing but what? Fy of y by x is equals to the joint density function fxy of x comma y by the marginal density function of the random variable x fx of x. So these are the formulas for the conditional density function of the random variable x and similarly of the random variable y in case of what type of conditioning? Point condition. There is nothing but the random variable takes a single value or specific value. Now this is for what? Continuous random variable. Similarly, if you want for discrete random variables, then how can you write down the conditional distribution function fx of x by yk? So what do you mean by fx of x by yk? It means the conditional distribution function of the random variable x such that the discrete random variable y takes a single value y equals to yk. Here both x and y are which type of random variables? Discrete random variables. So for discrete random variables, how we are writing here? The conditional distribution function fx of x by yk is equals to what? Sigma I equals to 1 to n p of xi comma yk into u of x minus xi by yk. So before going to this, first you'll see. So what is fx of x by y equals to yk? That is nothing but what? P of x less than equals to x intersection, okay, yk. So what is fx of x by y equals to yk? That is nothing but what? P of x less than equals to x intersection yk by p of yk. Previously I have seen what is fx of x, p of x less than equals to x. Similarly, what is fx of x by y equals to y? Yk, then nothing but what? P of x less than equals to x by y less than equals to yk. And what is p of a by b? P of a intersection b by p of b. So in place of a, x less than equals to x. In place of b, y equals to yk. Therefore, p of x less than equals to x intersection yk by p of yk. Now, we can write this as what? P of x less than equals to x comma y equals to yk by p of yk. Now, this is called as what? The joint distribution function of the random variable x and y. Therefore, this is nothing but fxy of x comma in place of y you are having what? Yk. So, fxy of x comma yk. So, we know the joint distribution function for discrete random variables. How can I write down here? The joint distribution for discrete random variables sigma equals to 1 to n p of xi comma here. Actually, the joint distribution function of two random variables x and y for discrete random variable. How can I write down here? Sigma I equals to 1 to n, sigma j equals to 1 to m, p of xi comma yj into u of xi minus yj. So this is what the conditional distribution, the joint distribution function for discrete random variables. But what about here y? Here the y is take any value, but here the y is taking a single value, a specific value yk. So here yk is constant. Therefore, this is what this term will be constant. Then what can I write down here? P of xi comma yk into u of x minus xi into, okay, u of x minus xi into u of yj minus u of y minus yj. So I'll write down again here. U of what here? U of x minus xi into u of y minus yj. But here the random variable y taking a single value, a specific value. Therefore, in place of this, what I get here? Yk minus yk. What is u of yk minus yk? U of 0. What is that value? 1. Therefore, what can I write here? Sigma equals 1 to n p of xi comma yk into u of x minus xi by, here p of yk is a constant value. The probability is such that random variable y takes a y equals to yk. Therefore, p of yk is constant. Therefore, by p of yk. So this is what the conditional distribution function for discrete random variable x and given the conditioning event y equals to yk. So how can you obtain the conditional density function? By differentiating the conditional distribution function, you are going to obtain the conditional density function. Therefore, fx of x by yk is equals to what? So differentiation of this. What is the denominator here? P of yk. Yk is a constant value, a single value. Therefore, it is a constant. Therefore, the denominator is constant here. What about the numerator here? P of xi comma yk is a probability into differentiate with respect to x. Then what is the differentiation of u of x minus xi with respect to x? That gives what? The impulse function del of x minus xi. Therefore, del of x minus xi. This is what the conditional density function of the random variable x, and given the conditioning event y equals to yk. And similarly, you can write down what? This is the conditional distribution function of x. You can write down the conditional distribution function of the random variable y and the conditional distribution density function of the random variable y such that x takes the conditioning event x equals to xi. So this is for what? Conditional distribution function and density function for both continuous random variable and discrete random variables in case of point conditioning. And what is the next type of conditioning here? Interval conditioning. So what is interval conditioning here? I am defining the conditioning event A such that the random variable takes an interval of values. For example, my y is from, let us say, 1 less than y less than equals to, let us say, 5. So I am defining the event A such that it takes only from 3 to 4. Let us say 3 to 4. It means it is taking some interval. Previously, in the case of point conditioning, my y takes only a single value. So like that, it is taking a single value. But in case of interval conditioning, the random variable y is taking an interval of values. Therefore, what is the interval? The conditioning event A equals to y1 less than y less than equals to y2. So it is same as the previous only, but in place of y minus delta y, you will get y1. In place of y plus delta y, you will get y2. That's it. But for point conditioning, this delta y equals to 0, therefore y equals to y becomes. So in the same way, you can write down the conditional distribution and density function for interval condition. Therefore, what is the conditional distribution function of the random variable x such that the conditioning event, the random variable y takes y1 to y2 is equals to what? P of x less than equals to x. Let us say this is B and this is A. Then what is P of B by A? P of B intersection here, A by P of A. Therefore, P of x less than equals to x intersection y1 less than y less than equals to y2 by P of A. What is A here? y1 less than y less than equals to y2. And this is nothing but what? The joint distribution function. So, fxy of x comma, and what about the y here? Y is taking from y1 to y2. And what is P of y1 less than y less than equals to y2? Nothing but what? The distribution function of the random variable y such that y is taking from y1 to y2. So, from the properties of the distribution function, how can I write down here? That is nothing but what? Fi of y2 minus fi of yn. And similarly, from the properties of the joint distribution function, how can I write fxy of x comma y1 to y2? That is nothing but what? fxy of x comma y2 minus fxy of x comma y1. And from the properties of the joint density function, how can you write down this equation? fxy of x comma y1 less than y less than equals to y2. Previously I have written. So from the properties of the joint density function. So what is fxy of x comma y equals to integration minus into x and integration minus into y, fxy of u comma v du into dv. So what is x here? Nothing but what? P of x less than equals to x comma y less than equals to y. It means x is less than equals to x is nothing but minus infinity x. Y less than equals to y nothing but minus infinity to y. So, but in place of y here, what do you have here? y1 to y2. Therefore, in place of minus infinity to y, you can write down from where to where? y1 to y2. And integration minus into x, fxy of u comma y into du into dy by, what is the denominator here? Fi of p of y1 less than y less than equals to y. Nothing but what? The probability of, is nothing but what? Probability of the event y1 less than y less than equals to y2 only. Okay, so from the properties of the density function, how can I write this is? So this is nothing but what? Integration y1 to y2 Fy of y into dy. So here integration Fy of y1 to y2, Fy of y into dy. And what is Fy of y? So Fy of y is nothing but what? The marginal density function. So how can you obtain the marginal density function? By integrating the joint density function with respect to x or the limits minus 0 to infinity, you are going to get the marginal density function. Now in place of Fy of y, you just substitute the marginal density function fxy of x comma y into dx. So what can you obtain here? In place of y, Fy of y, integration minus infinity, fxy of x comma y into dx into dy. So in place of x, replace it by u. In place of y, replace it by y. Then what can you obtain here? fxy of u comma v into du into dy. Or else, in place of this, you can substitute by v also. Okay. And this is what the conditional distribution function in case of interval condition. Similarly, if you want the conditional density function, what you have to do? You have to differentiate the conditional distribution function. So by differentiating this conditional distribution function, you are going to get the conditional density function. Whatever the denominator is constant. Therefore, p of y1 less than y less than equals to y2. That is nothing but what? Integration y1 to y2 integration minus into infinity fxy of u comma y into du into dy. This is also called as what? Integration y1 to y2 fy of y into dy also. The denominator is equals like this also you can write it down. Okay. And whatever this is constant, therefore the denominator is constant. So you have to differentiate only the numerator here. So when you differentiate with respect to x, whatever here, then what can you obtain? Integration y1. The integration differential weight cancels. Then what can obtain here? Integration y1 to y2 fxy of x comma y. So fxy of x comma y into what? Dy here. This is a conditional density function for interval conditioning. Now, so we'll go for the properties of the conditional density function. So what is the first property? The conditional density function takes a non-negative value. And second condition is, what is the second property here? Always the conditional density function area is equals to 1. There is nothing but what? The area under the density function, the conditional density function is equal to 1. And what is the third property here? The conditional distribution function of the random variable x can be written in terms of the conditional density function. And the fourth property states that the conditional probability of the event A, here the event, okay, the random variable x takes from x1 to x2 and the conditioning event A is equals to what? Integration x1 to x2 fx of x by a into dx. It means already we have seen the properties of density function. What is the first property here? Always the density function is a non-negative value. And what is the second property? The area under the density function is equals to 1. And the third property is what? The distribution function of a random variable x can be written in terms of the density function as fx of x into dx. And the fourth property we have seen is what? P of x1 less than x less than equals to x2 is equals to what? Integration x1 to x2 fx of x into dx. So these are the properties of the density function. And the same properties you can apply to the conditional density function also. Just in place of x, here what is you are getting? You are getting the conditioning event x by a. The conditional probability x by a. The conditional distribution function x1 by a. Similarly, here also the conditional distribution function, density function fx of x by a. That is nothing but. Okay. Now, how do you prove this? So, the area under the conditional density function is equals to 1. That is nothing but what? Fx of x by a is dx is equals to 1. So, now we take the LHS side. So, integration minus into infinity fx of x by a dx. Now, how can you write down the conditional density function? It is defined as what? The differentiation of the conditional distribution function. That is nothing but what? fx of x by a by dx into dx. So the differentiate with respect to x and integration with respect to x. So both will be get cancelled. Then how can I down here? Fx of x by a, and what about the x limits here? Minus infinity to infinity. It equals to what? Fx of infinity by a minus fx of minus infinity by a. So what is fx of infinity by a from the properties of the distribution, conditional distribution function? 1. And what is fx of minus infinity by a? 0. It equals to what? 1. Therefore, the area under the conditional density function is equal to 1. And what is the next property here? The conditional distribution function we can write down in terms of the conditional density function as integration minus infinity to x1 fx of x by a into dx. So that equal, then we'll take the RHS first. So integration minus infinity to x. How can you define the conditional density function? By differentiating the conditional distribution function by dx into dx. Since both are with respect to x, then the differentiation integration will cancel. Then how can I down here? Fx of x by a, and what are the limits of x here? Minus infinity to x1. Therefore, what can happen here? Substitute the upper limit fx of x1 by a minus fx of minus infinity by a. That equals to what? Fx of x1 by a minus, what is fx of minus infinity by a? 0. Nothing but p of x less than equals to minus infinity by the value is 0. That equals to what? Fx of x1 by a. That is nothing but your LHS. And similarly, what is the next property? The conditional probability of the random variable x in the conditioning event a is equals to what? Integration x1 to x2 fx of x by a into dx. So let us prove this property. So first you take the RHS. So integration x1 to x2. How can you define the, what is the RHS here? Fx of x by a into dx. That equals to integration x1 to x2. How can you define the conditional density function? The differentiation of the conditional distribution function. So dx into dx. That equals to the differentiation with respect to x and integration with respect to x. So both will be get cancelled. Then you can write as what? Fx of x by a. And what are the limits of x here? X is equals to x1 to x2. That equals to what? Fx of x2 by a minus fx of x1 by a. So from the properties of the conditional distribution function, how can I write down this as what? P of x1 less than x less than equals to x2 by a. So therefore, what are the properties of the conditional density function? We can state as what? The conditional density function is a non-negative value and the area under the conditional density function is equal to 1, and the conditional distribution function can be written in terms of the conditional density function and the conditional probability of the event of the random variable x and given the conditioning event a can be written as the integration of the conditional density function over the limits x1 to x2. So like that, today we have seen the conditional distribution function and conditional density function formulae for both point conditioning and interval conditioning. After that, we have seen the properties of the conditional density function. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.